Okay. So when I was starting to prepare to give my lectures here, I asked Kun, how's the blackboard? And he gave the excuse that it's an experimental laboratory, and so they don't need a blackboard, and they don't have one. And so I prepared, as I often do, as many of you may have already seen, I prepare my blackboard-style slides, which are more actually whiteboard style. Okay, so in my first lecture here, I'm going to talk about many-body quantum dynamics of systems that thermalize. And we're talking about the dynamics of entanglement, the dynamics of operator spreading, and of thermalization. And so this will be, I guess, different than the previous two lectures, I guess, in two different ways. One, strongly interacting. Of course, Duncan was talking about strongly interacting systems, but he wasn't talking about highly excited systems. Steve was, well, I guess his systems might have been strongly interacting, but they weren't really many-body yet. Yeah. But what we've been looking at a lot recently is this very difficult regime of both strong interactions, high entanglement, and being highly excited, which had been to a large extent neglected, I think partly because people thought that when you take a system to high temperatures, it acts classically. And it's just not true. There's a lot of interesting quantum mechanics at very high temperatures, right? And that's part of what I'm going to be talking about. Okay, so the types of systems, it's very general, but the types of systems that inspire this line of work are condensed matter systems, many-body AMO systems of various types, and as Duncan emphasized, spin chains, just like in the types of stuff he was talking about, they're the simplest examples to think about, right? Many-body physics, spin chains is really a very great laboratory for learning a lot. So I'm talking about generic, local, non-integrable, chaotic systems. So nothing special about them. And we don't know how to solve them with any methods of theoretical physics other than exact diagonalization. One does theoretical ideas, conceptual ideas, some work with matrix product states, but this is, people are working hard on getting matrix product states to really work well in these regimes. And when I say highly excited, I mean really not at all near ground states, at energies that correspond to non-zero temperatures, and often we actually just work at infinite temperature. Right? If we're working with a spin-and-a-half chain, it has a bounded energy, and we can just look at the entire Hilbert space, and that corresponds to being at infinite temperature. Right? And there's a lot of interesting stuff happening at infinite temperature in quantum systems. And so this would be regimes where there's no quasi-particle description, so there's, it's a real fully quantum many-body problem. Okay, I'm going to talk about closed systems, right? So if my system is coupled to an environment, I'm just going to make my system bigger and include the environment, right? And so I have a closed system, right? Okay, and in general, that system will be in a mixed state, and so I'm going to describe things in terms of mixed states often, although sometimes pure states. So let's say the initial state is given by the density operator rho of 0, that's 0 time. And then if you go to later time, there'll be some time evolution operator which gives you the later time state. Right? Of course, we could write this analogous thing for pure states. And this is a unitary operator, okay? Fully reversible, right? Its adjoint does reverse it. And now what types of unitary time evolutions do we want to talk about? In fact, we've gotten very flexible about this because it's nice to consider lots of different types of unitary time evolutions. And so one of them is, of course, the one that's very familiar, which is e to the minus iht, a time-independent Hamiltonian. And this system will have a conserved energy. And it might have some other conservation laws as well. And another point is the unitarity of the time evolution we view as a conservation law. So there's one conservation law which is unitarity, and I'll say a little bit about that, and there might be other ones like energy here. Okay? Now, or people are often interested in flow-case systems where you have a Hamiltonian that's periodic in time, right? You might have a RF field on or a laser on, such your Hamiltonian's periodic in time. But the system's still unitary because whatever is making this Hamiltonian periodic, we're thinking of classically. It's not something you can get entangled with, right? It's some coherent state and you're coupled to it weakly, and we're ignoring any entanglement with that, right? So now we have a time evolution which is periodic in time, and we can, if the period is capital T, we have the unitary operator which takes you through one period of the time evolution, and then the unitary operator which takes you through n periods is just the nth power of that, right? Now these two both, the Hamiltonian has eigenstates which are time-independent states. Here this unitary operator has eigenstates which again would be stroboscopically time-independent states, right? That after one period they come back to themselves, and then they just do that over and over and over again, right? So those are two types of time evolution one might consider. Or we could just consider some non-periodic Hamiltonian. So, we look a lot at random quantum circuits, which look like this. Okay, so here across in the x direction, these are my degrees of freedom, numbered 1, 2, 3, 4, 5, 6. And let's say they're q dits with q states per site. And sometimes we take the limit q to infinity, which allows analytical treatment of such circuits. There's a nice paper by Nahum et al. I'll be mentioning. So Adam Nahum is currently at Oxford, and he pioneered a lot of this stuff, and I really like his work a lot, and I'm working with him now. So a quantum circuit would look like this. We have on site 5 and 6, we have some q state object, and then this gate U56 super 1, so that a gate coupling 5 and 6 at time 1, and it takes in the state from 5 and 6 and transforms it to some other state with a unitary. And then we have a different unitary here and here and here and here and here, and these unitaries might be drawn from some distribution. And in fact, often we just pick them completely Haar-random, which means they're just completely random unstructured unitaries. And that helps with the analytic calculations, right? And so now we have a unitary time evolution, discrete time, where there's no eigenstates, right? Because every time step is different. But it's still unitary, right? And it has a lot of the properties of the other ones, which are more physical. But this is a nice laboratory which is in some sense simpler for calculating things and getting some of the physics right, as long as you keep in mind there's some aspects of the physics which are different here because there's no eigenstates, so it's different in some respects as well. And one has to keep that in mind in this kind of work. Okay, so what kinds of questions do I want to address today? So for example, we might start with an initial state. Here I've drawn a pure state of low entanglement or low entropy. So it's a non-equilibrium state. And when I say low, I mean low relative to thermal equilibrium, right? And then the question is, let the system evolve under whatever dynamics I have. And a basic question is, does the system act as a bath for itself and bring itself to thermal equilibrium in the limit of long time, right? So there's two questions. First question is, what does this sentence even mean? What does this question even mean? That's a non-trivial question itself. And then what's the answer to this question once you know what it means, right? Yeah?
Prior question, what do you mean by low entropy? Isn't it entropy 0?
Well, which entropy? Okay, so there are many entropies. Yes, there are some entropies that are 0 for this state, and there are other ones which aren't, right? But let's say for some of them, it's lower than thermal equilibrium, like the entanglement entropy, or the diagonal entropy, or the thermodynamic entropy. Okay. Entropy is a human construct, and there are many entropies. All the good ones agree in the limit of an infinite system. But when you talk about small systems, they all behave differently, and it's not clear what's the best entropy to be talking about. And they're all good. They're different tools. Entropy is just a tool, except in the thermodynamic limit, where it's actually a well-defined physical thing. Okay. If so, what are the dynamics of its entanglement? How does hydrodynamics emerge from hydrodynamics, which is often irreversible and dissipative? How does that emerge from the reversible unitary microscopic dynamics? So some of these are very fundamental questions, and I think we're getting different viewpoints on them than were around before. Or, for example, rather than start with a state, let's start with an operator. Right? So here's an operator on my chain, right? And it's the identity operator on every site except the origin. So at the origin, I have a non-trivial operator, and everywhere else I have the identity operator. So that's my operator is the outer product of all these things, right? Normally you just call this A sub naught, but it's nice to think, whenever you're talking about an operator on a particular degree of freedom, you should always remember it's the outer product of that operator and the identity on everything else in the universe, right? It's always implicit, but sometimes you forget, right? And it's good to always keep that in the back of your mind, especially the kind of stuff I'm talking about today. Okay, so then we can ask, here's an operator. What does this operator become under time evolution, under the Heisenberg evolution of this operator, right? And so this operator evolves this way, right? And you can rephrase this question as to how does this system hide this initial operator, right? If I give this initial operator some expectation value different than thermal equilibrium, the system will go to equilibrium, and it'll forget that this was polarized. But of course, the time evolution is unitary, so the information that it was polarized is still in the system, right? Because nothing's lost under unitary time evolution. Right? And so that's what I mean here. How does the dynamics of the system hide this initially local operator? Right? Or we could ask, what does this operator, if I start with an initially local operator and look at it at later times, what does it look like when written in terms of the local operators? How does the operator spread? So what an operator generically does in an interacting quantum system, if it's an initially local operator, it'll spread in space inside a Lieb-Robinson cone, so at some speed of signal propagations, and it becomes within that cone highly entangled. And so this operator will schematically end up at a later time looking like this, where it's the identity far enough away from the initial site because the operator didn't spread that far, but in a region between, so that's V sub LR for Lieb-Robinson, so in a region near the origin, which is growing linearly with time, it becomes some rather complicated entangled operator operating on that region, right? Times the identity outside. Right? It's not strictly equal, as anybody who has looked at Lieb-Robinson will know, that there are exponentially small terms outside the Lieb-Robinson cone, but they're bounded. So that's why I put a not equals here, but a equals with a twiddle. Okay, so those are just some, that was the introduction, just to sort of give you a flavor of where I'm going. Questions? No? Okay, so the first thing I want to focus on is thermalization. Okay, what is thermal equilibrium? So thermal equilibrium, at least in thermodynamics or statistical mechanics, is the maximum entropy given some number of constraints. And I want to particularly be talking about systems where there's not a lot of constraints. So it's not an integrable system with an infinite number of constraints. It's just got some small number of constraints, such as energy conservation corresponding, and its thermodynamic conjugate is the temperature, or you might have particle number conservation and a corresponding chemical potential. So equilibrium would be the correspond to a given temperature, a given chemical potential, et cetera. But I haven't really defined it yet. So if you don't like what I've said here, it's incomplete, so be patient. So many systems do thermalize under their own dynamics. So we have some unitary dynamics, given by some Hamiltonian, which may be time independent or periodic in time or non-periodic in time. But anyways, as you go to long time, this dynamics does bring the closed system to thermal equilibrium in the limit of a large system, right? So thermal equilibrium as a well-defined thing It's only sharply defined in the thermodynamic limit, right? But there are many systems of interest that fail to thermalize, and the ones which we understand most are the integrable systems of various sorts. You know, a system that is integrable has an infinite number of conservation laws. That's, in some sense, what integrability is. And these systems, at least in some sense, do not thermalize. And one particular case of integrability is the case of many-body localization, where the conservation laws are actually localized operators, and I'll talk about that tomorrow, not today. There's also, you will see in the literature a lot, this word pre-thermalization. So pre-thermalization usually means the system actually does thermalize, but it takes an extremely long time. And before it thermalizes, some interesting long time regime happens where something interesting is happening, right? So some very long transient regime before thermalization, and this long transient regime is the focus of interest. That's usually what people mean when they say pre-thermalization. Not really, because often it's a critical thing with power laws. There's a lot of different examples of pre-thermalization, and
would you put a glass in a system that fails to thermalize?
Well, that's a matter of opinion. Yes, myself, but a lot of other people think the glass actually doesn't thermalize, and so yeah. But I'm not going to talk. I'm just mentioning here things that do not thermalize that I'm not going to talk about today. just to but today I'm going to restrict my attention to systems that actually thermalize well. They're what you might call quantum chaotic systems. They act as a thermal bath for themselves, and they do it reasonably promptly. And so we don't have to worry about failures to thermalize. And that's what I want to focus on today, because there's a lot of interesting questions already there. You would think, oh, the system goes to thermal equilibrium. What else is there to say? Right? The thermal equilibrium is is simple. What's left to say about it? But there's a fair amount left to say about it. Okay, so what do I mean? Now I'm going to try to define thermalization a bit more precisely. Okay. So let's say we have a time-independent Hamiltonian, since that's what you're generally more familiar with. And when it thermalizes, that initial state has a certain initial energy, and that energy is conserved, and you will thermalize to the temperature that corresponds to that energy, right? And if your initial state is some kind of Schrödinger cat state, which actually corresponds to different temperatures, right? It's some linear combination of one temperature and another, that system won't go to thermal equilibrium, right? Because energy is conserved, and part of the wave functions at one temperature and part of the wave functions at another temperature, and you're not going to get a thermal equilibrium, right? So to get thermal, when we say a system thermalizes, we mean it thermalizes from an initial state that has subextensive uncertainty in any conserved quantity, so that the conservation laws permit it to thermalize, right? Okay. So we're going to, and any state you could prepare in the laboratory without enormous effort has this property, right? To prepare Schrödinger cat states is extra work, right? Steve, I think, is going to talk about cat states later this week, although not, yeah. Okay, so we have an initial state which has an uncertainty in its energy and any other conserved quantity that's small enough so that in the thermodynamic limit it could go to thermal equilibrium. Okay, so now here's my system, and it's isolated. So this hatch here, that's the rest of the universe that it's isolated from. And I've got all these degrees of freedom inside this box. And then I look at a subsystem. So this small subsystem S is just some of the degrees of freedom, and S bar is all the other degrees of freedom, right? The rest of the system. And I have in mind this one's small and this one gets big. So when I take the thermodynamic limit, I'm going to keep this one finite, take this one to infinity, and then only after maybe take this one big. Okay? Okay, so now we have our full system, rho of t, which is doing this unitary time evolution. Okay, so that's the state of the full system, and it remembers everything about the initial condition because it got there from a unitary operation, right? But now I'm going to take a trace over all the degrees of freedom that aren't in this subsystem, and I'm going to call that the state of this subsystem. So the state of this subsystem is, what's the state of this subsystem ignoring everything else? just tracing it out, right? And so this is the density operator for the subsystem. And thermalization is that in the limit of long time and large volume of the system, this is equal to what it would be at thermal equilibrium. The subsystem has the same state as it would at thermal equilibrium. And one way of writing what it might be at thermal equilibrium is to do the same trace on the Boltzmann-Gibbs distribution here. But in the thermodynamic limit, we know, this is one of the powers of statistical mechanics, you learn about all these different ensembles, and they're actually different states, but they all have the same equilibrium properties, right? And so here, what you put here, and take the trace over all these other degrees of freedom to ask what the subsystem is, you could put whatever equilibrium distribution ensemble you want here, right? You could put, canonical, microcanonical, whatever, right? Because they all give the same answer if you look at a subsystem, right? And that's why you can choose whichever ensemble you want when you do statistical mechanics calculations. You choose whichever one is mathematically convenient, right? Because they all give the same answer if you do it properly, okay? So thermalization means, under the dynamics of the closed system itself, the subsystems go to thermal equilibrium. It doesn't mean the full system goes to thermal equilibrium, because the full system doesn't. The full system still remembers every detail about the initial condition, right? But the subsystems go to thermal equilibrium. And that's what we mean by thermalization. If the system is Hamiltonian or Floquet, and all initial states do thermalize, so the strong assumption of thermalization is it thermalizes for all initial states that satisfy this, that they're subextensive uncertainties in the conserved quantities. If our system has a Hamiltonian or it's Floquet, then we could choose initial states that are actually the eigenstates of the unitary time evolution. And they should thermalize, but they're time independent, so therefore they must have been thermal right from the start, right? And this is one way of motivating the eigenstate thermalization hypothesis. So the eigenstate thermalization hypothesis, first of all, it's a hypothesis. It's only true for some systems. It's actually false for a lot of interesting systems, right? So there's no theorem here. But it seems to be true for generic many-body quantum systems. It's only false for integrable systems or many-body localized systems. There are certain special cases that are not necessarily fine-tuned, but have special properties, right? And so for most physical systems, this seems to be true, that a large quantum system will bring itself to thermal equilibrium, right? And actually, so this was first cleanly formulated by Srednichi in '94, but in fact, it was first observed in this nice paper in Phys. Rev. Letters 1985 by Jensen and Shankar on a spin-and-a-half chain with 7 spins. And they noticed that all the eigenstates look like thermal equilibrium to the best you could with 7 spins. And they did observe that and pointed it out. But somehow people didn't really follow up on it seriously until 20-some years later. Okay, so the eigenstate thermalization hypothesis is that all the many-body eigenstates of the unitary time evolution are thermal. Right? So that if I put the full system in an eigenstate of its dynamics, the subsystems look like thermal equilibrium.
Is the converse true, that if that holds, then all initial states do thermalize? Or all ones that...
Well, you need conditions on degeneracies as well, right? So thermalization is a dynamic thing as well, and that seems to also be true, right? But you could have, a lot of eigenstates that were thermal. You could choose, right? If a system has massive degeneracy, you might be able to choose a complete set of states which are thermal, but they have no dynamics. So you could put a system out of equilibrium, and it would just stay out of equilibrium because they're massive degeneracy. So to really get thermalization, you also need conditions on the degeneracies and on the off-diagonal matrix elements to get the dynamics, right? So it's simple going from the assumption of thermalization to the ETH. And the full ETH actually has a bunch of off-diagonal conditions in it, which were stated a certain way by Srednichi, but he made them definitely too strong. And so I think right now we don't know what is the minimum off-diagonal conditions on ETH to get thermalization. I think that's still not clear. It's being investigated. But I'll say a little bit about, in fact, on this slide here. Any other questions? So if you have a system that thermalizes and ETH is true, then every individual many-body eigenstate of the dynamics, or the Hamiltonian, if it's a time-independent Hamiltonian, is at thermal equilibrium. So that means every such eigenstate is actually a fine microcanonical ensemble. So when you learn or teach the microcanonical ensemble in statistical mechanics, there's always this arbitrariness of what's the energy interval you use, right? The microcanonical ensemble is equal probability all eigenstates within this energy interval. And then if you ask, well, how do I set the energy interval? There's really no good answer to that, right? In the end, it doesn't matter in the thermodynamic limit as long as you keep it small, but there's no good answer to it. But in fact, there is a good answer to it. Pick just one state. That's perfect, right? Because the system has a natural scale, which is a single eigenstate. And if ETH is true, that eigenstate is a fine thermodynamic ensemble. So I call that the single eigenstate ensembles. And it's the natural limit of the microcanonical ensemble. And for a system satisfying ETH, it's a fine microcanonical ensemble. OK, so that's an interesting observation. If all the eigenstates of the dynamics are thermal, how do we make non-thermal states? How do we get ourselves out of equilibrium, right? If all the eigenstates are equilibrium, how do you get out of equilibrium, right? And so how does that work? So let's now write out the eigenstate. So here's my unitary time evolution operator. Here's the eigenstates of it. And since it's unitary, the eigenvalues are just phases, right? Okay. And so now let's take these eigenstates and write our initial state in terms of these eigenstates as a density operator, which is now a density matrix, because I've written it in a particular basis. So we got these rho NMs, which are the matrix elements in the density matrix. And to have a non-thermal initial state, what you need is these off-diagonal matrix elements have their phases chosen. When n is not equal to m, they have these are coherences in this basis, and they need to be finely tuned to make this a low entropy state, right? If I take a non-equilibrium low entropy initial state and expand it out this way, and these are all thermal states, these guys are going to be fine-tuned to get you to low entropy, right? And then what is the time evolution in this basis? It's just put in some phases. Right? That's all quantum mechanics does, is it just puts in phases, nothing else, right? Once you're in the eigenstates. So at later time, you just put in some phases, right? And at long times, what happens is these phases become essentially random. Of course, they're not random, right? They're the actual phases of the eigenstates. But if you go to very long time, to all intents and purposes, they're random, right? And so you've dephased this initial state, and that's enough to make it thermal. So that's the way thermalization works in systems that satisfy ETH, which is, as far as we know, almost all systems that do go to thermal equilibrium. You just start them off with some special coherences, and then it just dephases. So the slogan here is, equilibration is dephasing. It's sort of a tautology, because what does quantum mechanics do other than add phases, right? In the basis of the eigenstates of the unitary time evolution operator, that's all it does. It's just rotate phases.
So does that mean it's effectively diagonal in this basis? Or
for observables. So for accessible observables that aren't highly non-local operators.
Can you repeat the question?
Right. And that's the approximation one usually makes, right? So here, if this is a non-equilibrium initial state, these off-diagonal matrix elements here in the density operator are very important, because they are finely tuned to interfere constructively on a non-equilibrium state and interfere destructively on the equilibrium states, right? That's basically what happens when you're out of equilibrium, right? You're in a linear combination of a whole bunch of equilibrium eigenstates of the system, but the phases are such that you interfere destructively on equilibrium, and you interfere constructively on some non-equilibrium initial state, right? And that's what's happening here, right? And so, of course, if you approximate this density operator by just keeping the diagonal, you will get the physics totally wrong, right? Now, down here, those phases have been completely scrambled, so now the diagonal dominates, right? The off-diagonal stuff, there's no more any special constructive interference due to off the diagonal on the non-equilibrium states. And so down here, what's often done when you come to equilibrium is to replace the actual state with the diagonal state, where in the basis of the time evolution, you just keep the diagonal terms and throw out the off-diagonal terms. And that's a good approximation. Not because the diagonal terms, off-diagonal terms are small, because they're the same size and magnitude as they were here. Right? It's not because they're small, it's because they have random phases and they add up in such a way that any observable, they contribute a negligible amount to the expectation value. Right? Because they're not doing anything special to focus all the weight onto one particular non-equilibrium initial state. Yeah. And yeah. Sorry, yeah.
Are you assuming that the observable is measured at a particular instant of time, or the measurement is also spread over a certain amount of time? When you say
Either one, either one.
But if I choose my observable cleverly such that it cancels somehow these off-diagonal phases, then is it not possible to get?
No, but for a large system, the only observables that are going to do something peculiar like that are completely non-local operators, which are products, very highly entangled operators of many, many degrees of freedom that you would just never be able to make that observation, right? But you're right. Every piece of information that tells you you were out of equilibrium in the initial state is still present in the final state, and there's a corresponding operator, right? But the operator has just become something which is just totally impractical to observe. Yeah, because there's no loss. It's a closed system. There's no loss of information, right?
But presumably if you do any time average, then...
Yeah, time average will solve it, but I don't like that, because I think, it thermalizes at individual times as well. You don't need to time average. Yeah, time average takes care of it, because if you time average, these phases these things time average to 0, right? And so, but that's good, and that's the simple answer, but it's not necessary. In instantaneous time, the system's at equilibrium, right? You don't need to time average. Of course, time averaging makes the argument simpler. Yes.
Yeah, but
yes.
But also more believable.
Yeah, just only because it's simpler. Okay, so that's sort of defining thermalization, not describing that much about the dynamics of how it happens, just going from the initial state to a very late time state, right? I didn't really tell you about what happened in between, right? Right, and so now I want to look what happens in between. So now the dynamics of thermalization, and well, there's many aspects of this, but two obvious ones, one of which is if you have any conserved quantities that were initially out of equilibrium, you're going to have transport and it's going to go to equilibrium. You'll have heat conduction and stuff like that. But this is an old and well-formulated subject. That's transport theory, and I have nothing to add to that. So I'm going to skip that, and and the new thing, and of course this is the topic of this school as well, is what is the dynamics of entanglement, right? So if the system is initially out of equilibrium in a way that it has entanglement that's different than equilibrium, how is that brought to equilibrium, right? And again, I refer to this nice paper by Nahum, which for me that's what really got me into this. Okay, so if you have interactions, remember I'm talking about interacting systems, generic interactions, and I want to discuss systems just with short-range and space interactions, not some real long-range interactions, just to keep things local. So we have generic local interactions, and this will increase entanglement. Right? You have two quantum degrees of freedom, and they interact. The generic behavior is they'll get more entangled. That's sort of the second law of entanglement, right? It's a special case where the interaction reduces the entanglement. Right? Okay. And so generic interactions will increase the entanglement until it is thermalized, maximized given the constraints. Okay, so I want to talk about entanglement, and of course Duncan introduced entanglement this morning, but let me just, okay, so yeah, this he said. So let's talk about a pure state now. We choose a cut, as he said, and now I'm going to look at the reduced density operator for system A, and we could do the same thing for system B, just trace over the other like that. So the entanglement, it's a property of the state and of the cut, right? So you cut the system. This is bipartite entanglement, like Duncan was talking about, and when you say the entanglement, you have to say what cut you're talking about, and completely broadly speaking, the entanglement is given by these two density operators, rho A and rho B. The density operator for A and the density operator for B. And there's a lot of information in there, part of which is the entanglement spectrum, which is the spectra of these operators. So these two operators actually have exactly the same spectrum in the non-zero part of their spectrum. If one of them has a bigger Hilbert space than the other, that density operator just has zero spectrum on the rest of the Hilbert space. So rho A and rho B have the same spectrum, and so there's only one entanglement spectrum. But then there's also the Schmidt states, what state in A goes with what state in B in the Schmidt decomposition. So entanglement's got an enormous amount of structure. And Duncan talked about some of that this morning. But I'm going to focus just on the simplest measure of the entanglement, which is entanglement entropy. Right? And there's two commonly used entanglement entropies, which are the von Neumann entanglement entropy, which is minus trace rho log rho, where rho is the density operator of one of the subsystems. And the other one is the second Rényi entropy, which is minus the log of the log of the purity, which is the trace of rho squared. There's also Rényi entropies of other orders, but the second one is the easiest one. The second Rényi entropy is nice because sometimes, well, it's just technically an easier thing because it's just something squared rather than a logarithm. That's an easier operation. Often theoretically it's easier, and certainly in the laboratory it's easier, right? And so you can actually measure the second Rényi entropy by just having two identical copies of the system, and then this is an observable. And that's been done experimentally, as I'll mention. And probably Rajibul might talk about that in his lecture because he actually did that experiment. Okay, so let's consider a finite 1D system in a particular state. So now it's 1D, and I'm going to cut it at x. So it's a system of length L, 0 to L, and I cut it at x. Okay? And so that way, in its state, I have a time evolution of the state. And so now I have, I have an entropy, either von Neumann or Rényi. Think von Neumann. I have an entropy which is now a function of the location of the cut and time. And in one dimension is nice because if you're just going to cut it spatially, there's only, the cut is simple. It's just which bond did I cut, right? Whereas as soon as you're above one dimension, the cut is a curve, right? And so this would, in higher dimensions, this x would be a surface of one dimension less than the full system, right? And so it becomes a functional, but let's just do 1D because it's simpler. So we have this is now a function of the position of the cut and the time. Okay? Now to look only at entanglement dynamics, I'm going to assume that if there are any conserved densities, they're at thermal equilibrium. And in fact, if you want to study entanglement and entanglement alone, that's one of the reasons we like these random circuits of these Floquet systems. If you want to study entanglement and entanglement alone, which is an interesting thing, it's good to get rid of all your other conservation laws because they tend to do their physics and it makes the situation more complicated, right? And so we like to work with systems that have no conservation laws at all, just because that way you can focus only on the entanglement and not get distracted with other aspects of the physics. Okay, but you can just say all the other degrees, all the conserved quantities are already at equilibrium. Only the entanglement's out of equilibrium, right? That's another way of doing it in a system that has conservation laws. Okay. Hi.
Is it always possible to find a wave function which has all conserved densities at equilibrium, whereas entanglement is?
I think it usually is, yeah. Usually you can just make a product state like that. And I don't mean at equilibrium on every site. I'm doing a coarse grain picture, so I don't necessarily mean exactly at equilibrium on every site, but in a coarse grain sense at equilibrium. Right? Because we just don't want to be dealing with effects of long distance transport, which will give additional flow dynamics, right? So usually you can find a product state that does that. And then it has zero entanglement, but everything else is near equilibrium. And then the only thing that has to go to equilibrium is the entanglement. There's probably cases where that's not straightforward to do. But
is it also not possible to just study a system without conserved densities at all?
yeah, that's like the Floquet system. If you have a Floquet system without any conservation laws, because it's time-dependent Hamiltonian, it has no conserved energy either. So the Floquet systems, or the random circuits, have no conservation laws unless you put them in, right? You can put them in, but you can also have no conservation laws at all. And that's nice, at least for a theorist. Yeah. Okay, so we're gonna assume any conserved densities are at thermal equilibrium, so we don't have to worry about conventional transport, but the entanglement is initially subthermal in some way, right? And the simplest thing is just start some product state. Now, right, I'm talking about a closed system, and if I start with some initial state and evolve it forward in time, it'll go to equilibrium. But if I take that same initial state and evolve it backward in time, it'll also go to equilibrium because the dynamics is reversible, right? There's nothing special about forward in time or backward in time. What's special about forward in time in our universe is that's moving away from the low entropy initial condition. Right? That's what we call forward in time, is moving away in time from the low entropy initial condition. Right? And it's a convention to call that positive time. Right? And I'm going to do that. But all the dynamics I'm talking about, if you went backwards in time, you'd see exactly the same thing as you see going forward in time, because I'm talking about reversible dynamics. Right? So anyways, I don't know if you had noticed earlier I was putting absolute value on the time, but I'm going to stop doing that. Right? And I'm just going to assume my time is positive. Okay, so what does the entanglement look like when you're at thermal equilibrium? Okay, so once you're at thermal equilibrium, here's what the entanglement looks like. So that's the entanglement as a function of the position of the cut in equilibrium in a large system. This is what's called the Page curve. What is it? Okay, so if we're at thermal equilibrium, what's going to happen is the larger of these two halves of the system, two parts of the system, is serving as a bath and bringing the smaller part to thermal equilibrium. And the smaller part will have the equilibrium entropy density, which is some equilibrium entropy density times its length. Right? So in this picture here, A is at thermal equilibrium, and it has the entropy density of A, and it's of length x. Right? And that's this point over here on this curve. And as I make A longer, the entanglement entropy goes up because we're making a bigger system. But then once I get past halfway, A and B switch roles. B is now the system and A is the bath. And then the entropy goes down because we're making B smaller, because B is smaller, and so it has smaller entropy. Right? Just because the entropy is proportional to the volume if you're at equilibrium. Right? So this is what, in one dimension, what the entropy looks like at equilibrium as a function of the position of the cut. Right? And so you have this result that at equilibrium, the derivative of the entropy with respect to position is equal to the equilibrium entropy density. Right? And so these two slopes, plus S equilibrium minus S equilibrium, that's the equilibrium entropy density, and that's what equilibrium looks like. Right? And here, nothing's happening to the entanglement. It's already at the maximum value, and so you can't produce more entanglement. The dynamics won't change this entanglement profile, right? But when if you're not at equilibrium and your state is such that the partial derivative of the entanglement entropy with respect to position, absolute value, is less than the equilibrium value, now at this location, the system is not maximally entangled, and the dynamics will produce entanglement generically, right? Entanglement happens. That's just the generic behavior of quantum systems, that if entanglement can be increased, it will be at some rate, right? And so from this, we get a coarse-grained entanglement, quote, hydrodynamics, which looks like this in one dimension. The time derivative of the entanglement at a given position, if locally the spatial derivative is not at its maximum value, you will have local entanglement production, and the entanglement production rate is some function of the deficit of the entanglement from equilibrium, or some function of this. And then we take out the equilibrium value here just for convenience. So this is the leading hydrodynamics of entanglement production in one dimension. The time derivative is some function of the first space derivative. And then it's a hydrodynamic, so it's an expansion in derivatives, and so there's higher order terms, like the second derivative, there will be higher order terms, right? But if you're talking about the leading behavior, this is what it is, right? Okay, so this function gives the local entanglement production rate. And this idea here is in the older papers of Nahum, but we're writing a paper right now, which hopefully will appear not too far into the future, talking about this more generally.
So you pulled out S equilibrium, so gamma doesn't depend. Gamma somehow is some universal thing?
Well, gamma has some nice properties, which I'm going to show you on the next slide, which are nicer to state if I pull it out. But before I go to the next slide, just to comment, this is the entanglement dynamics if all the conserved densities are at thermal equilibrium. More generally, this dynamics will be coupled to the conventional hydrodynamics, which is transport of all the conserved quantities. And this function here, gamma, will depend on the local temperature and the local chemical potentials and things like that. So this is just the entanglement dynamics in this simpler situation. But the more general hydrodynamics would couple this to conventional hydrodynamics. Yeah?
When X is a finite fraction of a half of the system,
Yeah.
why does B serve as a bath for A? They're comparable in size. I thought that you needed B to be much, much larger than A for it to serve as a bath.
No. No, that's what Page did this calculation, and when you're within one or two sites of the center, it breaks down. So there's a correction as I go away, and if you have, right, okay, so this is one of the cases where whether you have a conservation law or not, okay, so if you had a conservation law, then the entanglement, what you're saying would be a bigger correction. But still, this is the volume law part of the entropy of A. So the part of A that's proportional to its volume. And that'll be fine all the way up to half, right? There are corrections. If you have energy conservation, the energy of A is anti-correlated with the energy of B because energy is conserved. If A has a high energy, B has to have a low energy. And this reduces the entanglement. So there's such corrections. And that's actually one reason why it's nice to get rid of the conservation laws, because it gets rid of some of those corrections. But yes, you're absolutely right. It's not this is not exactly equal to the on the level of order 1 to the equilibrium energy density, because if B is only 2/3 of the system and A is 1/3 of the system, it can't fully thermalize it. But those corrections are sub-extensive corrections, right? And right now I'm just focused on the leading behavior. But that's a good point.
So maybe, David, to rephrase a little bit, so your curve was actually two straight lines. It's not a real cusp.
There's a little rounding here at the top.
But the size of that rounding
is order 1.
Yeah, it's not a function of the size
Yeah,
of the system.
right. So this cusp here is rounded at the top with order 1. And in fact, you can see why, right? Because at the very top, it rounds out, and this derivative is 0, and you should have entropy production. But you don't, because the second derivative term is big. So right at the top, this second derivative term is very big, which I'm neglecting. And this term and this term cancel to give equilibrium and no entropy production even at the top, right? And so there's order 1 stuff happening here at the top, which is interesting, but I'm doing the hydrodynamics coarse-grained, and we're going to treat that as a cusp on the resolution we're looking at. But yeah, there's interesting stuff happening if you look more finely. Thanks. Okay, and this is not meant to be true for all states, right? I have a given state. There will be states which violate this dynamics. This is kind of like the second law, or this is like transport equations or whatever. It's a statistical law. It's true for almost all states that you would produce, but you could make special states that will do something very different, right? Just like, if you take a given state and evolve it forward in time with minus the Hamiltonian of the system, and then let it evolve with plus the Hamiltonian of the system, it'll go down to low entropy because it's just reversing what it did before, right? So if you reverse, right, if a system is increasing its entropy and you reverse time, the entropy will go down. But that's a very finely tuned state, right? And that's not a generic behavior, right? And so this is meant to apply to a state that is not finely tuned and has had some dynamics, and it's just doing typical behavior of a many-body state. Nothing special, no cat states allowed. Okay, so there's that basic hydrodynamics again. And now I wanted just to address what you said here, or what you asked. So this function here, which is the entropy production rate, which is a function of the entanglement derivative in space, right, has various properties. First of all, it's non-negative because of that's just the second law. The second law is about entanglement production, second law of thermodynamics. If we believe the universe is quantum, all entropy is entanglement entropy. For reasons that I don't want to get into, this function is always convex. It's like a thermodynamic function, and so it has to be convex. It goes to 0 at the two limits. That's because the limit of positive, these two limits of plus S equilibrium or minus S equilibrium are equilibrium, and there's no entropy production at equilibrium because you've already maximized the entropy. So it goes to 0 at the two limits. The value at 0 slope is what people call the entanglement speed, right? That's a speed which quantifies how entanglement gets produced when you start from a product state. And then the slopes, for reasons which aren't at all obvious at this point, and I'll say a little bit about later, the slopes of how these come in at the limits here and here are the so-called butterfly or Lieb-Robinson speed, which is the fastest speed at which signals of order 1 can propagate in the system. Okay. And convexity, given this and this, convexity tells you that the entanglement speed is upper bounded by the Lieb-Robinson or butterfly speed. Okay. Okay, so here are just some examples about this. So one thing people often do is just start with a product state. So just start with a state where every degree of freedom is put in a pure state and there's no entanglement. That's a product state. But then there's a Hamiltonian or a unitary which couples them and they become highly entangled under the dynamics, and they go to equilibrium, which is a highly entangled state with a lot of entropy. So you start with, so this is now a different time. So you start with S of x and t equals 0, 0, right? And the ds dx is 0, and so the entanglement will be produced at a rate given by this times the entanglement speed, and this will just come up. But at the ends here, it can't go above equilibrium. So equilibrium is this line here, the page tent, and you know, at this value, we've got the right end of the chain at this cut maximally entangled, and it can't go any higher. So basically, the hydrodynamics just gives this form where it just comes up, it gets more entangled, and reaches the maximum at the edges, and these things here at the edge move in until they meet at the center, and these guys move at the entanglement speed, right? So for this case, starting from a product state, the entanglement thermalizes as if entanglement is spreading with speed, this entanglement speed, right? And this actually was a big distraction for me, and I think the whole field, is people were thinking of entanglement as something that moved, right? And I was certainly distracted by that, but it's not true. Entanglement is just produced locally at a cut. The entanglement production at that cut is constrained by what's going on nearby, but entanglement doesn't really move, right? And so looking for a speed of motion of entanglement it's a little bit confusing because there really is nothing moving. It's just a constrained nonlinear equation like this, right? And you get shocks that move, but it's not really the entanglement that's moving. It's just some feature that's moving, right? Okay. But anyways, that's there's a conventional definition of the entanglement speed, and that turns out to be the value of this. And it's really the entropy production divided by the equilibrium entropy. Data just like this was actually produced in a beautiful experiment from Marcus Greiner's group, Kaufman et al. Science, where they did this for the second Rényi entropy, which they could measure by. So they started a 6-atom, 6-site Bose-Hubbard chain in the product state of just 1 atom per site with no hopping. And then they turned on the hopping, 2 identical systems, turned on the hopping, and then interfered them with each other to measure the second Rényi entropy. And they measured it as a function of the cuts, because they could do it at every cut. And they got data like this, although it's a rather small system, so it was a lot of finite size effects, but it's a beautiful experiment. And so you should take a look at that if you're not familiar with it.
Can I ask you a question about where you want?
Yep, back.
So if I take your equation at the top and then I want to apply it to the initial state, and then I'm going to get this structure.
Yes.
Do I need to say something about what's happening at the corner?
At the shocks?
Yeah.
No, you don't. It's kind of like Berger's equation that way. It makes shocks, and they're fine. Now, if you want to, the dot, dot, dot contains second derivatives, and the shocks will actually be rounded out, and you could do that too. But if you just leave them out and just let them be shocks, discontinuities of the first derivative, that's correct. Correct coarse-grained physics. It's it's like Berger's equation, which makes shocks, right? And that's once you put in the rounding of them, nothing really changes. All you do is just put in the correct rounding of them, but nothing changes outside of that region.
So little s jumps on your top plot.
From 0, yeah, it's 0, and then it's the equilibrium value.
It just
Yeah, yeah.
discontinues.
And so that means, that's actually an interesting point, is this is very easy to measure, and this is very easy. So this point, and this point are very easy to measure. But this whole curve is actually a challenge, right? And so we've been doing numerics on various spin chains, and we would like to have a nice plot of this curve. But it's actually tricky to set up an initial state in a small system with a certain entanglement gradient that's not like some peculiar state, and have it evolve long enough to see the equilibrium entanglement production rate, right? And so there's really only 3 points on this curve that are straightforward to measure in a small system or in an experiment. And the rest of the curve is kind of tricky.
I mean, what about some kind of quench, like in CFTs, people always do these quenches, you start one Hamiltonian and you change the Hamiltonian. So your initial state is not unentangled.
Yeah. In principle, that would be fine. Yeah.
But it just has a different entanglement than the equilibrium one.
Yes. Right. And if you can do analytic calculations and do a big system, you can do that and then get, Yeah, I think this curve can be calculated in CFT in certain models where you can do those kinds of calculations analytically. Yeah, but I'm not aware that it's actually been presented yet. But I'm sure that'll happen soon. Yeah.
Very nice very small region, it will.
Yeah, it just goes to equilibrium, and it can't get more entangled than equilibrium.
But some of the argument is very clear why you would also get it on the side which is closer to when the size of the subsystem is closer to L, because you're all in all in a pure state.
Right.
But the physics is kind of surprising a little bit. That the large system will also equilibrate very quickly.
What do you mean?
Well,
I don't know what you mean.
So the first regions to equilibrate are either the small system or the.
No, no, no. It's just this is this little system at this end, and this is this little system at this end. So this is A equilibrating, and this is B equilibrating. And they're both small. They're both small. It's symmetric. It's perfectly symmetric in all.
I agree. But because the whole system is in a pure state.
Right.
The S of the system and the complement is the same.
Right.
So you could also think about.
Oh, okay. So
large
you're saying
system.
if I go here,
Yeah.
as far as the entanglement entropy is concerned, this side of the system looks like equilibrium.
Right.
But of course it isn't, because if we know it's not really at equilibrium, because we know it's in a non-equilibrium state. Yes. But it's sort of, it had to, because it's a pure state and this side's in equilibrium, and so the entropy had to be correct on this side as well.
But it's a very
But
small.
but it's not really equilibrium in the sense I'm talking about. Well, yeah, I see your point, but yeah. Okay, so here's another. Go on. Yeah.
So let's imagine a physical system like a 1D spin chain.
Yeah.
And I start in a product state and let it evolve.
Yeah.
Is there some physical quantity which VE corresponds to the spreading law, or?
Other than that, that's a physical quantity, right? The entanglement across a cut is a physical quantity, and it has a cusp in its curve, and it's moving at VE.
Is there something I can visualize in terms of the spins which is spreading at VE?
Well, it's that there's a point beyond which the entropy of the right-hand half of the right-hand portion of the system is already at equilibrium, right? And that front moves, right? But it's right. That's what I'm saying. That's why I put quote on spreading, right? Is because I don't know. I agree with you that it's not clear that there's anything really physical that's moving at that speed, right? It's sort of, it's very different than normal transport theory, right? You're talking about a density and it's actually flowing, there's a current, and that's something's really moving, right? Whereas here, this is a different kind of hydrodynamics, right? It's a hydrodynamics of a more low, the entanglement is a non-local quantity, right? And so its hydrodynamics is different, right?
But if you looked at like the expectation value of a local observable, would it have a kink as a function of time or something when that wave passed through? Or?
No. Yeah, that's why I think it's, what's his name? Hong Liu calls it the entanglement tsunami, right? But it's the most gentle tsunami ever, right? Because you would never notice it come by, right? Because the local observables, nothing happens, right? You can only see it by looking at the entanglement entropy of the whole system, right? Yeah.
But even though sort of before that time,
And that was actually the misleading thing. He called that entanglement tsunami, and people really took that seriously. And it sounded like there's actually something moving which you could observe locally, but it's just not true, right? And I think that was a big distraction for us. And it was this paper from Adam Nahum, which he said very clearly, it's entanglement production, not entanglement motion or transport. It's production, and I think that's right. 10 minutes. Okay. So maybe I'll finish my first lecture tomorrow. But I hope you guys are having fun. I actually like I put the good stuff in my first lecture so that if I don't get to my second lecture at all, it's fine, and we'll post it, right? I'll post the slides for my second lecture even though I might not get to it. So here's another nice example, and this is where you see the Lieb-Robinson or butterfly speed. So now, instead of starting with a product state, what I'm going to do is I'm going to take the left-hand half of the system and the right-hand half of the system and put them both in equilibrium pure states, which are fully thermalized, but they're not entangled with each other at all. And so now I have two of these page tents, right? So this side's at equilibrium, this side's at equilibrium, but there's no entanglement between them. And now I turn on the coupling between them, and that equation does this. So the entanglement propagates up this slope and up this slope on this curve here being the Legendre transform of this curve. And this little kink here, which is a discontinuity in the second derivative, moves with the butterfly speed, right? And that's the fastest you can get a feature in the entanglement profile to move, right? So this is the system's speed limit for something that, is actually propagating and not exponentially decaying, is the Lieb-Robinson speed, right? And so the Lieb-Robinson or butterfly speed can show up in one of these profiles if you take the right kind of initial condition, and this is an example of that. Okay, so these results I'm telling you about are obtained analytically for random quantum circuits in a Q equals infinity limit, where you can do the calculations analytically so random circuits with completely random unitary gates acting. And then when we do numerics on more realistic models like Hamiltonian spin 1/2 chains, everything is consistent with what I'm telling you, but of course the systems are very small, right? We're talking about the dynamics of very highly entangled states, and so this is something you can only do it with exact diagonalization, because we're actually exploring what happens when you go to very high entanglement, and so the size systems you can actually do this for is rather small. But we have a scenario, and to the extent we can test it numerically, it appears to be true. And it was actually inspired a lot by numerical results we got for such systems, and then we said, oh, how does this make sense, and can we understand it? And we think we have a pretty consistent picture. Okay, so shall I take it that some of the question period has already elapsed? Who's in charge? You are.
I'm in charge.
Yeah.
Yes.
Yeah, I think I got a few questions during the talk, right? Yeah.
So let's, do you want to stop here and take some more questions? Is that what you're saying?
Well, no,
Until
can I go another few minutes?
You can go another 5 minutes, and then we'll
Okay,
take an urgent question at the end.
Yeah, Greg didn't set the clock back. Where's your managerial skills? He's good at giving orders but not taking them. Okay, so the next thing I want to talk about is many-body chaos, and I want to talk about many-body quantum chaos, but first I want to talk about many-body classical chaos, because this is something that isn't, there's actually a bunch of interesting stuff in the literature from the 80s and 90s which pretty much escaped everybody's attention, right? And we had to discover it. Okay, so first I want to look at classical spin chains. So say we have a spin chain with classical spins, right? So with some Hamiltonian dynamics, so it satisfies Liouville's theorem and Poisson brackets. So it's just like a quantum system, but classical. But it's got all that symplectic structure. Or it could be an anharmonic oscillator chain. It's got enough nonlinearity so it's chaotic, right? Okay, and there's a paper just recently posted about the Heisenberg spin chain. So the Heisenberg chain with unit length spins, classical is a nicely chaotic system. Spin 1/2, it's integrable, but as soon as you leave spin 1/2, it's non-integrable. Duncan's spin 1 chain is a nice chaotic system at high temperatures. Okay, so the time evolution, again, it's classical, but we can still do time-independent Hamiltonian, or we could do Floquet, or we could do a random circuit of classical gates. You can do all the same things, right? And you have what's called the butterfly effect. This is where the butterfly name came from. And the way you do that is you consider two initial states that differ infinitesimally only on one site. Okay, so now I'm talking about classical states of Newton's equation type classical dynamics, where the state has no entanglement. It's a product state of local states on each site, right? Okay, and so we can take two initial states that differ infinitesimally only at the origin, right? So my S now is not entropy, it's the spin variable at each site. And so we have a difference between my two states, which at x equals 0 and time 0 is 0, but everywhere else it's 0, right? Okay, so we have two states, they're highly excited states. They're going to both be very chaotic, and they're exactly the same everywhere except on this site, okay? And now we're going to evolve them both with the same Hamiltonian. It might be time dependent, but they're getting the same Hamiltonian, exact same Hamiltonian. And then we measure the resulting difference. Somehow the projector is starting to crap out on me. And so we just look at the derivative of the difference between the two states with respect to the initial difference that was made, right? So this is just an infinitesimal difference, and how does it get either amplified or suppressed as I move away in space-time? Okay? So the difference spreads and it grows within the Lieb-Robinson cone, but it's of random sign, right? So both states are doing something completely chaotic, right? And so this perturbation, whatever it was, looks like a random perturbation later on. So if you just average it, you'll get 0, right? And so we square it and then average it, right? And this is the classical out-of-time ordered correlator, right? A classical analog of that. So we just take the difference and square it and average it, and then we'll get something non-zero, and that'll tell me, did my perturbation at the origin have an effect at x and t? And how big was the effect in magnitude, right? And so this is, and this is the analog of a quantum out-of-time order commutator, like if I take an operator at the space-time origin and commute it with another operator at some other space-time point, and then look at the norm of the square of that commutator. Right? This is an analogous quantity, right? To quantify the chaos. Okay? And what happens? So what happens is, if it's a chaotic system, the difference will grow exponentially. Chaotic systems, classical chaotic systems, small perturbations grow exponentially, right? At least some components of small perturbations grow exponentially, other ones decay exponentially, so that the total volume of the phase space is preserved, but some of them, half of the components of the initial perturbation will grow exponentially, right? And as they grow, if we do chaos in an extended system, as they grow, they will spread as well, right? And so you get a velocity-dependent Lyapunov exponent, right? And this is the first place I found it was in Lieb-Robinson. They were talking quantum, but they had a formula like this. And then this was Kaneko 86 is a nice earliest discussion I've found of this for classical chaos. So this is now my perturbation squared. So this is my out-of-time order commutator. And if I go out at a fixed speed from the initial perturbation, so x equals vt, this will either grow if we're inside the Lieb-Robinson cone, or decay outside the Lieb-Robinson cone as a simple exponential function of time at late time with some coefficient lambda, which is the velocity-dependent Lyapunov exponent, right? And the Lieb-Robinson speed is the speed at which the velocity-dependent Lyapunov exponent is 0, so the perturbation neither shrinks nor grows. It can remain of order 1. And so that's the fastest speed at which an order 1 perturbation can spread without decaying, right? And that's, since it's first in Lieb-Robinson, we should maybe call it the Lieb-Robinson speed, but people are calling it the butterfly speed these days. And inside the Lieb-Robinson cone, the Lyapunov exponent is positive. The difference grows exponentially. And if you have a non-chaotic system, you still have a Lieb-Robinson speed. It still decays exponentially outside the cone, but inside the cone, it doesn't grow exponentially. It typically does some power law or something if it's an integrable system or non-interacting particles or something like that. Okay, so it looks like I should stop. I made it to slide 12. So, many more.
You're back on tomorrow morning, it looks like, right?
So we'll do slide 13. We'll start with slide 13.
So let's thank David.
Whoops, actually I should.